Swayam Prabha. Digital India. Educated India.
Hello, welcome to yet another session of our NPTEL on Nonlinear Adaptive Thinking. I'm Shrikant Subramanian from Systems and Control IIT Bombay. So we just started the 12th week of our lectures in this NPTEL course. So this being the final week, I sort of started off a little bit with a little bit of history of how adaptive control evolved. And this is what we were looking at until this time. So, if you, so we were looking at this paper by Annaswamy. This is a paper that, of course, I will post. And we are essentially looking at the chronology of how things evolved. Uh, we, of course, saw a few things on how you started with the requirement for adaptation. Then we had this optimality based MIT rule, and then there was a need for stable adaptive control. Beyond that, we also had null reference adaptive control, nonlinear adaptive control, and epsilon sigma modifications, parameter learning. But then there was also this parallel world where there was development for this stochastic discrete time systems. Then there was the notion of learning, which was uh, like neural networks, Adeline filters, which involved parameter estimation again or weight estimation again, and then there was notions of reinforcement learning, which involved the use of neural networks to estimate some value functions and so on. And so overall, uh, there is a lot of parallel developments where the notion of parameter learning was playing a rather big role. So this was sort of what we have seen. I quickly want to wrap up our discussion here on this paper. Of course, I will put this up. We have not even discussed half of the article, and it's very difficult to discuss it in entirety. Um, but a lot of it are things beyond this. A lot of it are material that we have covered in this course, and so it should not be very difficult for you to follow. So this is where I start my lecture 12.2. Right? So um, one of the problems that, of course, started to be discussed in parallel with the evolution of adaptive control was the pattern recognition and classification problem. So in this, what happens is that there are usually two classes, A and B, um, and here there is basically some features which are denoted by xk, and there is an output which is denoted by yk, and usually these outputs are in the form given in equation 21. So this framework was, of course, in Yakubovich and Novikov also. Um, so the um, you know what we want to do was to classify these images, right? And so the question that was sort of asked is there um, is there such a are such of these the possible to separate these classes by a hyperplane, right? And what does it mean to classify objects or these images into a hyperplane means asking the question of whether there exists some parameter thetas and theta naught such that you can write this output in this linear relationship with the parameters. So this is this, and of course this phi is some suitable kernel function or regressor in our adaptive control framework, right? So how this works is you sort of expose the model to a lot of features, and the goal is to learn this value theta 0 so that you can classify any further images after the learning process into classes A and classes B, right? So uh, and of course, I mean, how you separate them into classes is, of course, I mean, you look at this value right here, right? I mean, whether you get, if you get 1, you are in class A, say, and if you're -1, you are in class B, right? So that's how you do this classification problem, right? So this is the image classification problem. But then in recent times, you would have seen sort of data classification problems also, right? Um, so uh, the interesting thing is now again this problem is reduced to identifying some parameters, and of course you can use this gradient type algorithms in order to find values for these parameters to a pre-specified accuracy, of course. Okay. And of course there are many gradient type solutions such as the one you see here, which is, you will see that it is not very different from your adaptive feedback law or adaptive update law theorem, right? This is just in discrete time, but has a very similar feel to your adaptive update, right? So, so of course there is this, I mean, um, this sort of interesting idea. Of course, there's an alternative approach where you choose some vector of weight such that this corresponding hyperplane is a supporting hyperplane to the convex hull of all these vectors, right? So you sort of construct these vectors y, x, k, phi, x, k, and then you sort of find these hyperplanes that are supporting hyperplanes to the convex hull of these vectors, right? So so then and of course, so that the minimum distance from it to the convex hull is uh, maximum, right? So this is sort of how the support vector machine methods were uh, had come about. But then you also see that there is this alternative method that we discussed first, and these uh, are sort of closer to what we do in adaptive control, right? So anyway, so um, then there was, of course, also the notion of reinforcement learning or adaptive dynamic programming, right? So I'm going to highlight this, that the fact that reinforcement learning is essentially adaptive dynamic programming. And why is that? The idea is that you have some, nonlinear evolution, and then you have what is called a control law, which is called a policy in this discrete uh, dynamic programming framework. So policies, essentially you have different control values at different instants of time, mu1, mu2, and so on. And then there is this notion of a performance index that you want to minimize. This performance index is like an infinite series or infinite sum, yeah, of this value function g, right? Um, right? So, and then j pi is called a cost function. And the idea is to find the optimal, right? You want to find the optimal. And where is optimal, if you see that you can see that it is indexed with a pi, and this pi is this policy. So it's an optimal with respect to the policy. So you find the control law, if you may, yeah, or a control policy says that this infinite sum is minimum. So you have to choose. So it's not just one choice of controller in discrete time. It's actually infinitely many choices, right? So you have mu1, mu2, mu3, all the way to mu infinity, because you can see that this is an infinite sum, right? So um, so then, in order to sort of look at this problem, how dynamic programming does it, and of course, this is the expression for J pi star. You can see that it is infimum with respect to the control policy pi. Right? So, using the Bellman's optimality principle, what you can the value iteration process is essentially organized like this. So, the optimal, how you read this is that the optimal at the k plus 1th time is simply the infimum over all control values admissible, admissible control value. So ux is the control admissible control set. So the admissible control means that suppose your control is to be bounded between absolute value of control has to be less than 1, so that would be this set. So you essentially look at the infimum over all control values of the function g and the optimal cost at the kth edge added to it. So this is how you sort of progress from one step to another in order to find the optimal control for that step. So this is the optimal value of u for that step. So, of course, to solve this, there is a very large number of function computations to be done. And so the idea here is to use a neural approximation for the function jk, and that essentially is approximated using, as always, a regressor phi, yeah, and a set of parameters wk. So you again see that there is a set of unknown vectors wk, which are weights, in this case called weights, and then there are phi's, which are some truncated basis functions, right? And these are used to uh, approximate the value function. This is what is the basis for doing reinforcement learning, and this identifying these weights is what is the adaptive part of this. This is the connection with adaptive control, because you see that again I have some parameters that need to be learned. I mean, you can call them weights, but eventually they are parameters that need to be learned. The only problem here is that um, uh, if there are disturbances, then talking about stability is rather difficult, because you know um, you sort of have to, if you want to look at stability and evolution of trajectories, you have to integrate over all such trajectories, and this has to be some kind of Monte Carlo method that has to be introduced, and therefore it is very difficult to I mean, come up with stability conditions for a closed loop system. I mean, there are of course some results out there um, that talk about these, but that is of course not a part of this article that we see here, right? So anyway, so this is sort of where we stop our little bit of a history lesson. Subsequently, there is many other sections in this paper on solutions in adaptive control and so on and so forth, and a lot of other interesting topics that have been covered in adaptive control. So it gives a little bit of a flavor of everything there is in adaptive control. Some of this, of course, we have covered in our curriculum here, and some of it we have not. So I would strongly encourage you to look at this article to get a good idea of where we stand in terms of adaptive control and how it's connected to learning. What I want to do now is to again go to another article, if you may, right? Uh, okay, I don't know why I have to pay this or that. I apologize. All right, so I want to sort of go here to this article, and this is an article from 1996 from Frank Lewis uh, and co-authors, and this article actually talks about implementation of an adaptive controller via multi-layer neural network, or an adaptive controller via multi-layer neural networks. And this is being used as a robot. So this is probably one of the first multi-layer implementations of neural network adaptive control in neural networks, with nice tracking, stability, performance results. Yeah, which is so. Therefore, I sort of wanted to look at this article with you in this last week, so that you can get an idea of how actually stability guarantees in neural networks can be provided. Yeah. So again, you see that this is an old article, and this is a rather specific article. We look at real-time application of neural network. In a lot of literature that you see now, or a lot of applications that you look at now, most learning algorithms are offline implementations, in the sense that the entire training of the algorithm happens offline. Right? But this is one of the few uh, results that you will see, especially connected to control, where you have online learning of the adaptive controller also. Now, uh, one can of course question, the advantage and disadvantage of either. Of course, it is true that if you do offline training, you can take in a lot more data and you can do much better learning of parameters, and learn probably for a larger variety of cases and so on. But one of the problems is that with with this offline learning and then implementation online is that if your initial conditions and your um, of your dynamical system and your operational conditions of your dynamical system changes a lot, right? Then for example, if I did a lot of I wanted to look at a sector and I want to fly my unmanned vehicle using uh, some images, right? Image processing, right? And I made a map, for example, in dawn, at dawn time. So I did all my training at early morning, and I use images that I obtained using an early morning flight, a bunch of early morning flights using this UAV. But then suppose I fly my, I actually fly my UAV in the evening time where the light is a little bit less, or maybe in the daytime where the light is a little bit more. Then the results become significantly different. So if the initial conditions, operational conditions change from the training data, then your performance can significantly deteriorate. On the other hand, if you are actually using some kind of an online uh, learning of this neural network, then you can continue to learn even when things change, and you don't deteriorate your performance significantly. So that's one of the advantages. But of course, the limitation is that you can only have a few layers, for computational efficiency, and and in order to be able to implement things in real time, right? So that's the idea. We are looking at a real time implementation of a multi-layer neural network, and we do this in the adaptive control framework that we have seen. Right? So, so a lot of uh, results have been written about this adaptive neural network, and but there is little about the use of neural network in direct closed loop networks. Okay? At least until '96, there is a little bit more now, but again, not a lot. Yeah, this is still an open area of research, especially the part about proving stability. Yeah. Uh, so one of the issues is sort of that need to be addressed adequately is the inclusion of ad hoc controller structures and the inability to guarantee satisfactory performance. So uh, so one of the things that is required in a lot of articles that these authors mention is that you need initial estimates for the neural network weights in order for performance to be good. Yeah, and identifying such stabilizing weights may not be very easy, yeah, before you even start running the system, right? So the idea in this article, as the authors say, is to confront these deficiency for full nonlinear three-layer neural network with arbitrary activation functions. Of course, there is concepts of robot control get discussed here a little bit because the application is a robotic manipulator, and the tracking performance is guaranteed using Lyapunov approach, even though there is no ideal weights that is identified. And typically, when you use a standard adaptive controller for a robot, right, the regressor matrix that is used in all these needs to be very tediously computed for every specific robot. For example, if I go from a 3-link robot to a 5-link robot, or you go from a linear joint to a articular or a rotary joint, things change significantly. So you have to compute the regressor matrix very carefully in order to apply an adaptive controller. Right? But the advantage of using a neural network based adaptive control is that it will automatically learn these parameters, right? So these using these activation functions. So it can be applied for any serial link robotic arm. Okay, so this is the advantage. One controller works for any serial link robotic arm, just like a package. Yeah. So one of the things that is sort of demonstrated in this article is that the standard tuning using back propagation based methods yields can yield unbounded neural network weights, um, and especially when there is disturbances, and the robot arm is more than one link, which is sort of a very very basic requirement that the robot arm may have more than one link. So there are modified weight tuning methods are also proposed here, which of course select the epsilon modification. Yeah. So, um, so the modified weight tuning approaches also, the authors claim that they can avoid the P condition, um, which is also something rather good, rather strong, right? Rather a strong result. Now, um, so let's sort of start looking into what the problem setup is, right? So we know that we are doing learning using adaptive methods. So typical neural network parameter estimation algorithms can rely on some kind of again gradient descent type formula, some kind of optimization based formula. But here everything is based on adaptive control and Lyapunov based results, which helps us to prove stability and closed loop performance, which will not usually be guaranteed in a optimal framework, right? That in the standard framework for offline identification of these parameters. Okay. So the other thing, of course, is that we do online identification and online tuning of the neural network. So that is another thing that we are looking to do. Yeah. So we do this, um, in a particular framework, and this framework is what we are going to look at. Yeah. So we already know what are all these real numbers, Rn and Rm cross n and all that. One important thing is that we're looking at functions f which go from some compact connected set in Rn to Rm, and the set of continuous functions in this space S is denoted as CMS. Right? Um, then we've already seen the notion is infinity norm. So this is essentially the supremum norm is the same, right? It is similar. In fact, it takes the any norm of the vector norm of the function, and it takes supremum of that over all the x in S. Over all x in this domain, you take the supremum of the vector. Yeah? So this is what is called the supremum norm. Then there is the Frobenius norm. We also saw this when we were looking in at model reference adaptive control. So the Frobenius norm of a matrix is just the square of the Frobenius norm is the trace of A transpose A. Right? It's not a vector norm. It's actually just it's essentially looking at the matrix as a vector and computing the it somehow vector transpose itself of the matrix by stacking the matrix columns into a vector. But of course, it's not a vector. It's not an induced norm the way we've defined induced norms. I hope all of you remember. But it is in fact compatible with an induced norm. Right? So if you take the 2 norm of Ax, then it is less than equal to the Frobenius norm of A times the 2 norm of X. Right? So this sort of inequalities are rather useful, right? Whenever we do sum of square kind of decompositions or some Cauchy-Schwarz step inequalities we want to use in a Lyapunov analysis, you know that these kind of inequalities are very useful for us. Right? Of course, we say that this matrix A of t is bounded if the infinity norm, induced norm of this matrix is bounded. Right? Excellent. Now, we want to, of course, see what a typical neural network looks like. In this case, we are looking purely at the three-layer neural network. So there are 3 layers in the sense that there is an input layer here, there is an output layer here. So all these, let me be careful. Yeah, so there is a input here, there is a hidden layer here, and there is an output layer here. Yeah, input, hidden layer, output. Yeah, whichever way you want to look at it. Yeah, so anything in the middle of input and output is called a hidden layer. Yeah, it's as simple as that. Yeah, because it's neither the input nor the output, so you don't look at it, so it's the hidden layer. Okay, so this is the 3-layer neural network structure. These Vijs are the weights here, Wijs are the weights here, and then you have these sigmas, which are basically like activation functions. So this is how a neural network works. You have some n1 inputs going in, then they are scaled by some weight, right here, and then they are summed up because you see there is a summing action here because of everything goes into everything else. So every input feeds into every every node, if you may. So there is the scaling, and then there is the summing action over these n1 nodes, and then there is an offset which is added. right? And then it passes through this activation function. So I think it's better to write it as this. So the activation function acts on this, and once the activation function sigma acts on this, it again goes to the second layer. So of course there is again weights, right? And that's the weights here. And then then there is again a summation. Sorry, and then there is again an offset, and then there is a summation. All right. So this is what is the output. Right? So you can see that uh, you have an input layer, a hidden layer, and then an output layer. All right. So this is what is the three-layer neural network: one input, one output, and a hidden layer in between. Right. So there is one activation function sigma. All right. So uh, uh, so we have several things you can see that are already unknown. What a typical neural network implementation would try to identify are these offsets and these weights, because once I identify these offsets and these weights, of course these are these n1s and n2s are pre-chosen quantities, right? So once I identify these offsets and these weights, I have an almost exact relationship between the input and the output. Okay, so don't get confused by our control systems terminology. The input is not the control, output is not the output of the system, and all that. This is for any nonlinear function. It's for any nonlinear function which is getting approximated in this. If you take any nonlinear function, it can be approximated in this. And that's the whole idea. And that's the whole idea. Now, in this case, we are doing the real-time neural network implementation. Therefore, we want them to exhibit learning while controlling. Yeah, we are not okay with learning first and then finding some parameters, good value the parameters, then using it for control and so on as a separate problem. No, we are looking at jointly learning and control. Now, what are standard choice of these activation functions are these like sigmoidal functions. These are like sigmoidal functions are like smooth signum functions. Hyperbolic tangent functions, we already know hyperbolic tangent functions. We saw them for the purpose of projection based adaptive controllers. And then you have these radial basis functions. These are essentially like the functions that you see in this bell curve and normal distributions and things like that. Yeah. So all these are very nice functions for function approximation. That is why these choices are made. It's not just arbitrary functions. I wouldn't take a linear function here for sigma. Yeah. So all these functions are somehow uh, functions that help you to do good function approximation. Yeah. So how we want to write this whole equation one is in a very compact, again, parameter regressor form, right? So this looks like a, I would say, nonlinear parameter regressor form. This looks like a nonlinear parameter regressor. Why? So how we do this is, first of all, we define our x with an x0. So you see there are n1 x's here, but I add one more x to it as x0. Okay. And then what I do is this sort of lets you to accommodate this thetas, okay, in this V. So the first column of V contains the threshold theta WL. Right. I'm sorry, I was here. So if you have x0 chosen as one, vector of one, then you can include, this threshold vector into the V's. Right. So if you look at, then if you compute V transpose X, it should be evident to you that because the first column of X is 1, yeah, then, sorry, because X0 is 1, not first column, because X0 is 1, if I choose the first column of V as the theta V's, then this is exactly what I have inside. And similarly, I can do for the W's also, right? I take this sigma activation function, but again, the first term of this activation function is chosen, is just written as 1. So the activation function, of course, if I write it as sigma z, that for a vector, it's assumed to operate element wise, sigma z1, sigma z2. But if I make the first element to be 1 here, then I can incorporate in W this offsets also. And once I do that, I can actually write y equal to W transpose sigma V transpose X, which is essentially like a nonlinear parameter regressor form. All right. So nonlinear because both W and V are parameters. It's not like a y theta equal to u kind of a thing. Not as simple as that, but a little bit more complicated. Yeah. So any tuning function, basically W and V includes all the thresholds and the offsets and everything. Right? So that's the idea. So great. So what did we see in this session? We sort of finished our discussion on this very interesting article, which chronologically discusses how adaptive control developed, how it got connected with learning, how reinforcement learning and deep neural networks essentially are parameter doing parameter identification in a different framework. And now we've started to look at the basic problem of doing real-time neural network based control of a robotic manipulator. And here the neural network weights are going to be adjusted using our Lyapunov based adaptive control theory. And that's what we are sort of trying to set up the framework for that. And in the subsequent session, of course, we will continue to look at this. All right. So I hope to see you again soon. Thank you.